before I bring up my slides, I'll just give you a little bit of information about me. Like Susan said, I'm at the NOAA Paleoclimate office just down the road, and I'm a postdoc there, so I'm doing some research on abrupt climate change, looking at computer models and comparing it to proxy records. My background is I did my PhD in oceanography at Texas A&M University, and I've actually been, when I was 13, I decided I wanted to be a marine biologist, so I kind of hit it close somewhat to the mark. Okay, so I'll just go through a brief outline, or just tell you I'm going to, kind of define abrupt climate change, and then talk about some of the mechanisms, which you guys have already talked about some this morning. I've heard various mention of these types of mechanisms that can cause abrupt climate change. And then I'll go through some evidence and examples of abrupt changes that have happened, and between both the paleo record and the instrumental record. And then I'll just briefly talk about impacts of abrupt changes. So these are a couple of the formal definitions of abrupt climate change. There's two that have come out in the last decade or so. The National Research Council has defined it as it occurs when the climate system is forced across some threshold, triggering a transition to a new state at a rate that is determined by the climate system itself and faster than the cause. So it's all big wordy, but basically the rate of change is faster than what caused it. And then more recently, the U.S. Climate Change Science Program has defined it as a large-scale change in the climate system that takes place over a few decades or less, persists for at least a few decades, and causes substantial disruptions in human and natural systems. Now this is for this report, this was very specific as saying a few decades or less, because there are some historical abrupt changes that, again, as we said before, abrupt doesn't necessarily mean, when we think of abrupt, it would be a very short period of time, day after tomorrow kind of scenario. Whereas, some abrupt events, it can be 100 years for it to happen, and it's still in the geological time frame, and that's what somebody was saying earlier, is it's hard for students to kind of get that idea across about, in the geological time frame, an abrupt 100-year event is a very short period of time. Just to go over this real briefly, you guys have already talked about weather versus climate. Weather is what's happening out right now. Climate is, a larger spatial time scale, the average weather. And I've seen an example of, climate is how many sweaters you have in your closet. And weather is whether you're going to wear your sweater today. This kind of thing. So it's putting it in a little bit of a perspective of that. So some of the mechanisms for abrupt climate change, and you guys have talked about this already this morning, are some of these feedbacks in the climate system. Most of the feedbacks, you have positive and negative feedbacks. Most of them in the climate system that would cause an abrupt change would be a positive feedback, which is, you have a small initial change that can eventually cause a large change, but it's always in the same direction. So an example of this would be the ice albedo feedback. So you get, if it's cold, say the North Atlantic, it's cold, you get more sea ice and snow has a higher albedo, you get more solar radiant, reflection, therefore it gets colder, you get more ice, and you're just this positive feedback. And you can also have a positive feedback in the other direction. You get warming, you get ice melt, surface of the ocean, land heats up, you get more ice melt. So that's still a positive feedback, but it's in the opposite direction. But that's a big example of some of the mechanisms of what can cause an abrupt change, because it's getting to that, that tipping point that you guys have talked about. Then one of the other mechanisms that's been proposed is, changes in the thermohaline circulation, what you guys have been talking about in some of this, the deep ocean currents and whatnot. And so if you have a lot of your deep water production is in the North Atlantic, and you're getting that's cooling and subducting, and which is kind of driving this ocean conveyor. And if you put a lid on that, if you either freshen it so it's more buoyant so it doesn't sink, or you put, you make it colder and you put sea ice over that area where it would normally subduct, you slow this whole system. And again, it's kind of reaching, it'll slow and slow and slow, and then it reaches that tipping point of where then you can have an abrupt climate event. So, and this is just my little diagram of kind of showing if you have how you get this abrupt event. If those two little cups on either side of the pendulum are two stable states, so the ball is either on one side or the other. It's either in one stable state or another. And if you push on one side, the ball will kind of roll, but it doesn't go into the other side. It just, rolls back into its stable state. So in the bottom, you have to really push the system hard to get it to fall into the other stable state. So, how do we know that climate can change abruptly? This is kind of going into the paleo record. You have the paleoclimate proxies, which, a proxy is, you look at various things that tell you information about like what the temperature was. We can't go back and measure the temperature. We can't go back and measure precipitation. But we have a bunch of different ways of looking at, I was told you guys did an ice core activity already. So you can look at ice cores and measure, the composition of the air bubbles in the ice core, or you can look at pollen or dust, or even how much between the annual rings to tell you information about snow and precipitation and temperature and windiness or dryness. Other examples are marine sediments and corals to look at ocean conditions, temperature, salinity, ice volume. A lot of lake sediments are used to determine kind of land, prior land, terrestrial variations. Again, a lot of precipitation and evaporation, because you get a lot of lakes where you have a lot of sedimentation based on runoff. So you can core into the lake sediments and you can see these annual varves of sedimentation. Tree rings, very well known one. And then a really hot topic, up and coming proxy, are these speleothems and cave formations that, again, you can measure and to determine air temperature or kind of moisture availability, precipitation, and things like that. And then these are just some fancy photos of the different types of proxies. And, I'll do my NOAA plug at the NOAA Paleoclimate website. We have all kinds of records of these various types of proxies that you can go back and look at, and ranging from corals, which are very high resolution, but just a couple hundred years, to the sediment cores that go back 65 million years. The photo here is the photo of the sediment core that they took where they saw the KT boundary. So this was taken out in the Caribbean, or the Gulf of Mexico, and so right right there, you can see that that is when the meteorite hit and it put all this up into the air and caused this mass extinction. And then as the, everything was kind of settling back out, you can see this variation in the sedimentation.
Could you just briefly talk about what they're looking for in those cave formations? Is it like length of them as a function of temperature, or they're looking at the composition of them to see what's going on here?
Yeah, if you're familiar with how they use corals to look at temperature, it's the same basic idea. They'll take. Okay, yeah, you'll take a slab out of either a coral or a speleothem, and it's a calcium carbonate. And so you can do isotopic composition, analysis, looking at the carbon and oxygen isotopes. And then with corals, you see the annual layering and you can measure their growth. So with the cave formations, it's the isotopes can be really tricky for temperature, but so they use them a lot to determine kind of this moisture availability and whether it was dry or wet, because if it's wet, you're going to get a faster buildup. So, and that, like I said, it's a really new proxy, and they're still trying to figure a lot of it out, but there's been a bunch of stuff that's come out in, especially with the monsoons in Southeast Asia and Australia and like Indonesia. Mm-hmm. I'm sorry. She asked how far back you can date the corals and the speleothems. For corals, if you take a live sample, a coral can live, you can get a couple hundred years, or some species you can even get, maybe 400 or 500 years if you're really lucky. You can find fossil corals, and if you can date those either radiometrically or in some other way, then you can, go back. There have been coral records that have been spliced together to give, a continuous record back to, for the last 1,000 years. And longer, there have been coral records that have been used to even document kind of past sea level changes. The speleothems, they grow or accumulate a lot slower. And to be honest, I don't know what like the oldest one is, but again, it's a lot higher resolution. Like the marine and lake sediment cores, you go back a lot further because your accumulation is a lot slower. So these accumulate faster, so you don't get as long of a record, but you get a lot more detailed information. So you can get, annual or whatnot. So, and then you just have like pollen. A lot of pollen records are also used from the lake sediment cores, and that kind of leads into some of this evidence for abrupt climate change. Yeah.
So are scientists putting each of these different proxies together to tell the story, or kind of looking at each one individually, or if one is more recent than we looked at in terms of year-by-year data?
Right. The question was, are scientists, do they look at each one individually, or do they try to compile the data to create a larger picture? And the answer is both. I mean, you get scientists that their focus and their specialty is one particular area, and that's the benefit of these climate data center website portals, is that you submit your data, and then somebody else, like for what I'm doing for my project, is I'm trying to take all the various records that have been reconstructed for a particular time period and combine them together and look at them. So you do get kind of both. There's not a lot of people that try to take everything because it takes so long to create one of these records that, but they try to share it so that other people can look at them. Was there a question?
I was just you said you put in your plug about you can get all this data off the website, and I was just sort of
If you Google NOAA paleoclimate, it'll be the first thing that comes up. And then there's later on, if you have questions about like actually finding data on the website, I can help you with that. So these are just a couple, squiggly graphs to show these evidence of these abrupt climate events. You can see on the left graph, between 5 and 10,000 years ago, there's a sharp drop in pretty much all of the various variables. You have temperature, ice accumulation, fires, and there's this real little dip, and that would be what's considered one of the abrupt climate events. I believe that's the 8.2 event that we'll talk about in a minute. And then on the right, this is just kind of showing some of the glacial, interglacial cycles. So from when you go to, ice age to non-ice age. So some of the examples that we'll talk about, and I kind of go from really large scale, long term, down to more recent and short scale. And again, on this is a really great, this is temperature reconstruction in central Greenland from an ice core record from 0 to 100,000 years before present. And so you can see that it was a lot colder, and then it started to warm up. You have that one little peak that's warmer, and then you drop back down, and that's the younger driest abrupt event. Then it starts to warm, and then there's another little dip, which is the 8.2 event. So with the glacial, interglacial cycles, this wouldn't necessarily fit the CCSP definition that I gave you at the beginning of it being, having to be a few decades, because these do happen over a lot longer time scales, especially the cooling. So, when you go from kind of a glacial period to a non-glacial, the warming is a lot more abrupt than the cooling is. And we'll talk about a little bit kind of the mechanisms behind that. But, an example, so just to kind of give you guys a little bit of the, this is several glacial cycles, and you have your July insolation and, Antarctic temperature, and then atmospheric CO2. So then another example, and I'll try to speed up through these, is the younger driest. This is probably one of the classic abrupt climate change example. And it's been recorded by numerous proxies. The hypothesized cause is due to this slowdown of the thermohaline circulation. This was during the deglaciation between about 13 and 11,000 years ago. You're adding a lot of fresh water to the North Atlantic. You're, again, kind of freshening this area, causing this global thermohaline circulation to slow down. You get this abrupt event that it cools, and like I said, it's seen in a lot of records. It's called the younger driest because it's named after the flower, because in Europe, they did a bunch of these lake core records, and they saw this time period where it was starting to warm, they were getting various vegetation, and then they see this sharp decrease or increase in this driest flower pollen, and it's a very cold species. So they assumed, climate was warming, and then all of a sudden it got cold again, this flower thrived, and then, then it continued to warm. And again, the younger driest, this was a very abrupt event. The end of it, records indicate that Greenland temperatures rose about 10 degrees Celsius in a single decade. So that really does, really is abrupt. Let's see. And so one of these other events is the 8.2 event. It's not nearly as widespread. It's not nearly as long, or even as the magnitude isn't as great as the younger driest, but it's a similar type event, again, seen in the ice cores where you have kind of these warmer Holocene temperatures, and then this blip in temperature that lasted only about, the maximum length was about 150 years. The real pinpoint was only 30 to 50 years. So it was a pretty short-lived event. Again, it's thought that it was due to slowdown of ocean circulation because of meltwater going into the North Atlantic. A more recent example of abrupt change that has a sociological impact is that it's been hypothesized the collapse of the Mayan civilization was due to an abrupt drought, dry event. And if you look at this, the middle graph here is oxygen isotopes from a lake sediment core. And the line up is drier, and that time of drying or aridity is at the time of the Mayan collapse. So there's no real hard evidence that this was the cause, but you just looking at the correlations of this dry period, this peak aridity, and the collapse, that's been one of the hypothesized causes for it.
Are there any theories as to why that got so dry at that particular time?
There are. It has a lot to do, which would be totally another talk. She asked about the reasons for why this arid time period. It would have a lot to do with the intertropical convergence zone, and that the way it shifts up and down, and if it's moving due to atmospheric conditions, that can cause that, especially that particular area of Central America, to become very dry or wet, depending on the position of the ITCZ.
Would that have anything to do to El Nino or La Nina circulation at all?
Yeah, she asked about if that has to do with ENSO, El Nino, La Nina, and yeah, it can. It can definitely be caused by that, and you'll probably hear more from Baylor this afternoon. You can get the ENSO, El Nino, La Nina, on shorter 5 to 7 year cycles, but then you get these longer term decadal cycles that are similar to El Ninos, but on a much longer scale, and I think it would be something more like that would cause a 200-year drought. And now just kind of getting, again into the shorter term record and looking at these and saying, okay, we've had these really big abrupt events in the past throughout the Holocene, and we even see these, shorter, not as major events, but in the more modern record. And this is just an example of some warming in the North Atlantic in the 20s and 30s, and scientists think that this could have been caused by some solar and volcanic forcing, and they saw a strong increase in ocean salinity and a decrease in sea ice in the Nordic seas. And then this graph on the right shows spawning stock biomass of herring in the Nordic seas. So if this region got quite a bit warmer, so between 1920 and 1950, the amount of herring increased a whole bunch because you had warmer water, so these fish were able to move up into this region where they normally were not found, at least at such large amounts. And then this bottom is just, is really seen in surface air temperature in Western Greenland as well. And the last example is again in the North Atlantic. And this region is talked about a lot because of the thermohaline circulation. There's so much happening that, and it's really thought that this can be the driver of major climatic episodes. So it's studied a lot and talked about a lot. Just real quick, there was an abrupt event, or a cooling and a decrease in salinity starting in about 1972. caused an increase, because if you have cooling, the water's denser, caused an increase in Labrador seawater formation, at which also you get more water sinking. It brings in warmer, salty, or, you know, as that happened, then finally warmer, saltier water began coming in the 90s. And then, you know, decreased this deep sea water formation. So they've seen it in the bottom graph is potential temperature, and the top graph are salinity anomalies. And just, you know, just to wrap up, again, you know, some of the impacts of these abrupt climate changes. Somebody had mentioned about, you know, the planting zones are changing, and, you know, ecosystems are extremely vulnerable to abrupt events because, you know, they can't get up and move. You know, we can, if we get sea level rise and we get flooding, we can get up and move inland or do whatever. But, you know, ecosystems, that's where they are. And so you get an abrupt event, and they either have to adapt to it or they die. And that's, you know, an example would be the dinosaurs. When you get that impact and you put all that stuff in the atmosphere, you change the climate abruptly, you know, those species, which was a mass extinction, cannot adapt that quickly. So, you know, that's one of the major impacts, is an ecological impact. And the flower on the upper right there, that's the driest flower, just because of the younger driest. So you get, and, you know, what's important for a lot of people now is the economic impacts of an abrupt change. Again, you get changes in planting zones or, you know, what can grow where. That's going to have an economic impact. And kind of going along with the ecological is the hydrological impact of abrupt climate changes. Again, you know, looking at the Mayans, you can get a large period of drought, or you can get a large period of flooding. And, you know, and there are tons of examples of impacts of abrupt change. But thank you guys for your attention. Again, I'm open to questions, or if you want to talk later. And that's my email address and my phone number. And, you know, you're welcome to contact me anytime with questions about this.